Hey everyone, thanks for joining. I hope you are having a good afternoon. My name is Banty Kumar and I'm joining you from Bangalore, India. I work at Uber as a software engineer. My role at Uber is basically to manage the MySQL control plane at Uber, and I want to talk to you about some of the problems that we faced, how did we fix them, and what we can learn from that. So this is a quick agenda. We are talking about what is the current MySQL scale at Uber. What are some of the challenges that we face? We will do a deep dive into one of those challenges. What are the optimizations and solutions that we thought of? And then I want to touch a little bit about sharding and bit tests. Cool. So I think some of you might have seen this slide. On this talk, I want to go a little bit deeper about what these numbers mean. Apart from looking nice into a slide like this, each one of these numbers actually signifies something for if you are managing a control plane at a company like Uber. So 99.99% availability, I think is pretty clear. Like we want our MySQL databases to be up at all times. But what does it mean to achieve this number? What do you exactly need this? What this actually means that you need a very robust failure detection and a mitigation strategy. Because when you couple this with the numbers above, it is impossible to achieve this without having a very good and a robust automation and a failure detection mechanism. So this basically means automation and a robust control plane. The numbers above 2600 clusters and 2000 nodes, what this means is that at this scale, whatever thing you want to do, no matter how small that is, it is impossible to do it manually. Like even if you want to change a MySQL variable, that becomes a task for you. You need a workflow, you need an orchestration to make sure that that gets applied to all of these clusters and all of these nodes safely, reliably, and you need some sort of a guarantee that it's there across this entire field. And to do this within this large cluster, it doesn't matter how small the task is, that how small the operation is, that task itself becomes huge. And what the second thing that it also means, it brings a lot of heterogeneity into your cluster. So what I mean by that is, when you have 22,000 nodes, at our current setup, we are running with 3 MySQL 8 versions. So we are running with 27, 34, and I think also 20 version. So there are 3 MySQL 8 versions running in MySQL. And believe it or not, we also have a MySQL 5.7 cluster running at Uber. So because the thing is, when we moved from 5.7 to 8.0, that migration itself was such a challenging work that we had to build a lot of automation, we had to do a lot of benchmarking. Every cluster has its own use case, has its own query pattern that is supported in 8.0, that is not supported in 5.7, something like that. So everything that migration in a way is still going on. The 5.7 is still there. There are so many clusters which are still fragmented. So now, let's say you are designing something, you have to make sure that your cluster, your database deployment is not homogeneous. Something can work in some cluster, but that might break in something else. That is what that 2 number also means. And 250 plus critical services at Uber, that basically means that your room for error is very, very less. No matter how small that error is, you might cost a lot of money to your business. So you have to be, the safety is your concern. You have to do everything very, very safely, and you have to think hard that what I'm going to do, is it going to cause any problems? So these numbers, even though looks very fancy in a slide, that actually comes with a lot of toil. And one of the things that we had to do was, one of the challenges is writer unavailability. Why that happens? So just to give you a picture, most of our setup in MySQL follows this architecture where we have a single primary, which accepts all the writes, and that gets replicated to whatever number of replicas. We have clusters with more than 100 replicas, and we also have clusters with just 3 replicas. But this thing here, this actually becomes a single point of failure, because if this dies, all your writes are gone, your cluster is facing an outage at that point. Replicas, we try to, the usage in replicas, we try to keep the CPU usage at around 30%. That is not a magic number. 30% is decided on the basis of the primary intention behind keeping it at 30% is to compensate for a failover, so that when we are facing some sort of a degradation in one of our regions or availability zones, we should be able to transparently switch the traffic to the different region, so that the business can go as usual. So the other regions should have enough capacity to handle that 2x load. That's where that 30% number comes in, because at the end, during the time of failover, it will have 60% of usage or maybe 70%, and that should be able to handle, a MySQL node should be able to handle that much of a traffic. So we have to focus just on this part here, this guy here. If this dies, then we are in problem. What kind of problem? And what is the root of all of this? Why do we care about this? Why do we talk so much about this guy dying? It stems from the fact that Uber believes in a philosophy, what we call as an impermanent infrastructure. What that means is that the infrastructure at Uber is very fluid. So there's a team, like the infrastructure team, do not care that your primary node is running on this host or what kind of traffic that node is handling. If a node goes down, they have the full autonomy to take that out of your entire infrastructure stack and place it into a different node. It lies, the responsibility of gracefully handling that decommission or replacement lies entirely on the storage team to make sure that your customers do not feel that the effect of that change that much. So, and what that basically gives us is that whenever there is an outage, like Uber lives on a lot of cloud, it also has on-prem, so anything can go wrong at any point in time. And what that impermanent infrastructure basically gives us an ability to switch our entire traffic from one zone to another zone without our end users even noticing about it. They would not even feel any latency difference. But that comes with a toil on the storage team to manage this kind of a problems. So when we started, this is this picture of around like 2.5 years back. The availability was less than 4 nines. What that means is that if your availability is less than 4 nines, you are not treated as a production ready database at Uber, because your primary failover time will be more than 5 minutes. In that case, you are not kind of eligible for tier 1 services. What I mean by tier 1 is your rides, Uber Eats, a lot of infrastructure services. You are not kind of eligible to be used as a database service for these kind of use cases if it's less than 4.9. We also were seeing like, okay, the leader is dying, but why does it die? When did it die? We also lacked a very extensive observability on this. And if you do not have this, you don't know what to act on. The second thing is, even like after we had the observability, we do not have the mechanisms, the automations to get out of that scenario in an automated fashion. Someone needs to get alerted. This is what we ran for around 3 or 4 months before we built all of this. Is what we just had is just have extensibility, observability to know that the leader is dead, and then it will page an on-call engineer. He will follow some sort of a runbook and then figure out, try to get a new primary elected and manage this 5 minutes of downtime, which, as you can imagine, was not a healthy practice. So we needed some sort of an automation, some sort of a control plane which can detect and do all of these leader elections automatically without even our on-call knowing about it. And once we had all of this, another problem that we faced was the limitation from a single leader itself. No matter how what is the availability of this? A single node has its own limit. It was not able to serve the ingestion load that was coming to it, and that's where Vitess comes into which I'll go over. And even if it was able to serve the ingestion, the replication lag that it was causing on these replicas was also not acceptable for some of our services. So to give you an example, the SLAs that we give to our customers is less than 5 seconds of replication lag, less than 1 second in the same zone, in the same region. And what I mean by region is that the hosts which are placed in a single building, which are not in a single building, they are part of the same software networking infrastructure. So the latency between the individual host is within 5 milliseconds. So for those machines, the lag would be less than 1 second, and for intra-region it is 5 seconds. This is the SLA that we give to our customers, and we need to be under that to be able to serve this kind of workloads. So what sort of optimizations that we did? So we first had to build our entire control plane, which for that detection as well as mitigation component. I'll go through this in the next slide. What this allowed us to do is it allowed us to have an automated leader election process, so that our on-call did not needs to be paged, and they don't have to do manual effort. And this also basically reduced our mitigation time from minutes to literally seconds. While building this, we realized that it is not good to, so we were relying on some external components to tell us whether the leader is down or not. We moved from that approach to a more aggressive health check via direct database pings. So we developed our own probers, which directly talks to the leader node, pings it for its health, and then takes a decision whether this leader is live or not. What that gave is it made our detection mechanism better, and it was able to find a problem in the leader node quickly. Against something which is running outside of MySQL, then it has to connect and find that problems. Now it is running with database, so that latency is very, very low. We also completely overhauled our entire routing mechanism around MySQL. Earlier we were using an object model, like we are using literally GitHub to manage all our routing information. What I mean by routing information is who is the leader, what is the host of the leader, what are the replicas, etc. We moved from that to etcd. etcd is basically a key value mechanism which also gives you watch events. So we moved from that to etcd, which provided both consistency on the topology changes, and also it was much quicker. And for the clusters which were on 8.03x, we also introduced the consensus-based leader election, which we saw in the morning talk. So this is a very, very simplified version of the availability optimization that we did. We had a leader node here, and then there is a health checker, which runs in the same container of this leader, which continuously pings the leader for its health. This ping is much more sophisticated, and what it does not just check whether this leader is able to run, let's say, a select one query. It also checks some MySQL variables which a leader node should have, for example, the read only. And it basically records all of these results into a log file running in a shared folder, which our other components can also read. Then we have a controller. You can look at this controller as an external observer, which can look into your MySQL cluster from an external perspective, just like your customers would do. And this is actually a very important call that we took, is the ping and the failure logs, etc., they have to be internal in order to do it quickly. But the detection has to be from an external observer, so that in case there is an availability zone partition, etc., the guy who is taking this decision, it should have exactly the same visibility as the users of this database should have. So this is an external observer which looks into these logs, and then based on the rules that we have defined, for example, if there are, I think, 10 failures in 5 minutes window, it takes an action to do a leader election in this particular cluster. So this is like a simplified view of the leader election mitigation strategy that we did. This helped us to improve our P99s from more than 5 minutes to 30 seconds, which brings us under the SLA of being a tier 1 MySQL cluster, being a tier 1 storage service at Uber. Now, what we were able to achieve because of this is that right now, the most of the Uber Eats homepage is driven by MySQL, both stores as well as items use cases. A lot of search functionality directly is powered by MySQL. Some of the offers and discounts that you see, that's all MySQL. Along with it, a lot of our internal services, which is directly responsible for bringing up or down the Uber infrastructure services, they all rely on MySQL, and they are all functioning in that way. So once this single primary multiple replica issues are kind of taken care of, now we went into another. So with greater, once it becomes a tier 1 service, now it started showing showing this problem, where basically the scale problem. Now everybody wants to use MySQL, but we have a limitation on the kind of node that we have. It can only have 48 cores and 300 gigs of memory. We cannot go beyond it. For that, we need additional approvals, which is not easy to get. So we have to work under that 48 cores. And with that, since our leader's resource is limited, the throughput that it can deliver is also limited, and that's where this problem comes in. When some of our Uber Eats use cases are getting onboarded to MySQL, we realize that the ingestion load that it comes with, for example, when a merchant becomes live, a lot of customers started to, when it becomes live, it has to update its catalog to MySQL. All of that events come to MySQL in a very, very small time, in a very small span of time, and that ingestion load was not being able to handle by a single leader. CPU bottleneck, because there are some because this is a master and replica setup, your reads are eventually consistent, but there are some use cases which requires a strict consistency guarantee, and for those kind of use cases, we recommend our customers to directly read from master. Now, at this time, the leader is serving writes, but it also serves reads, so the CPU usage increases even further. And for those sort of workloads, our throughput decreases even further. It also have a single primary node also have a strict disk I/O capacity. What I mean by that is that when a lot of writes come to your leader, even though if it's replicated to replicas, the replicas would take time to process all of those rows. We do a row-based replication, and this time would increase the replication delay on the replicas, and the SLAs that we talked about, we were not able to manage that. This was one of our biggest problems. The leader, even if the leader was able to handle the load, we were not able to keep our replication delay in check. And the number of replicas that you can add, there's also a limit there. And we knew that after a certain point, we cannot just keep on adding replicas to manage the reads. So in order to get around the challenges of a single node, we started looking into, so this is some of the limitations that we were working under. We had some clusters with 10 or 11 terabytes of disk, which is which is, I mean, it's fine, but it's very, very difficult to manage from a MySQL platform team perspective, because at this rate, everything becomes very, very slow. Like your backup restore will take a lot of time. When you're adding a new node to the cluster, the bootstrapping process will take a lot of time because it has to copy a lot of disk. So everything that you do becomes slow as your disk increases. So we actually recommend our customers to be inside, to be less than 500 gigs, but we were seeing 2 terabytes, and there was 2 or 3 clusters with 11 terabytes of disk, which is just insane. We could not go more than 48 CPU cores, as I mentioned, and the memory was also limited at that time to 192 gigs, but we increased it to 300 gigs, but that also was not enough. What that basically, once you reach to this limit, our infrastructure services starts to see some issues. They were not able to give us the nodes to manage this. Our MTTR, etc. are all increasing. MTTR is basically mean time to restore and mitigate. We were not able, so if there's a 2 terabytes of disk, you cannot take a backup and restore it within what most of our customers expect, which is 20 minutes, 30 minutes, even 1 hour. It was not possible to do it. In order to solve this problem, we started to look beyond the limits of a single MySQL node.
Just a quick question. Did you not consider just promoting one of the replicas to be a primary and rearranging the topology?
So we do that.
Okay.
So when the leader actually goes down, what we do is we elect one of the replicas.
Okay. You're talking about copying all the data and it takes time.
Yeah, so this is basically what I talked about, your impermanent infrastructure, right? So new nodes can come and go from the system at any point of time. You have absolutely no control over it. So when a new node when a new node needs to be replaced, what it does is an empty node comes in, and we use the Percona's extra backup to copy all the data from the new node, from the existing node to the new node, get it up to date with the replication, and then we let the node go away.
Cloning is quicker. Native cloning is quicker.
Okay, yeah, look into that. So, okay, so we needed something quick to first get rid or solve our single leader problem, and we were working with Vitess, but we will see that Vitess is not very easy to deploy if you are going on-prem, and we needed a solution for our application developers immediately. So what we, as a temporary solution, we went with an application level sharding. What this does is we still have independent MySQL clusters. They had their own control plane. These clusters did not know that they are part of a single shard setup. Our control plane basically binds that to a single shard, and then we also had a customized client which these services can talk to, and this guy, the customized client, understood the sharding key and everything, and based on the query that it gets, it identifies which MySQL cluster I need to send it to, and then sends it to that cluster. It is a very, very simplified version of Vitess's VT gate, which only works with one sharding scheme, that you can give just one key, and these MySQL clusters, even though they appear like a shard, they are not actually shard. They were all independent clusters, which made the control plane very, very complex. What I mean by that is, since these are independent clusters, they all need to have their own users. So when you have, let's say, 20 clusters, you need 20 users in your application. That's insane. The second thing is, if you want to do a schema change, you have to do 20 times. Everything basically you have to do that many number of times. So this is clearly not a good solution, and we needed to provide sharding as a platform capability, not like an application level sharding. Enters Vitess. This is just a normal introduction to Vitess. It's basically a cluster management solution for database using horizontal sharding. I'll share the slides, but what I want to cover more is why we chose Vitess. There were other applications we considered, but why we went with Vitess? And one of the most important thing that we considered is, which also ties me to the first slide here, what these numbers also mean, that whatever change you want to do to your database, it has to be transparent to your customers. You cannot call 250 customers of the service and say that you move from this database to that database. It has to be completely transparent to your customers, which Vitess allowed. The VT gate setup that we had, it allows MySQL protocol. So, and users can connect to it like they are connecting to MySQL. The sharding aspect is completely abstracted with them. And it also gave us a lot of ease on migration. So the migration is completely transparent. They don't even know about it. All they have to do is change one IP, which we are also looking to eliminate, so they don't even know that something has happened to the database. And overall, since the deployment strategy that Vitess has, it uses etcd for metadata, the VT gate and VTCTD or stateless services, VT tablet and MySQL can exist on our stateful nodes. So it was very easy to integrate with our ecosystem, even though it still took us 6 months to do that. So we went with Vitess, it's live, it's serving a lot of traffic, it has been going really well with us. But we also are planning to do some optimizations on Vitess. For example, the materialized views that it has, it's not, the push-based mechanism that it follows, it's not scaling well for us, and we are looking for a pull-based architecture. We made some changes in the VTalk to improve the leader failure detection mitigation by considerable amount. We have to develop durability policies which understands Uber's infrastructure details. That has also worked very well in a very recent incident that we had. We are also working on replication-based write throttler. That is also live, working very well, and then now we are also working on the consensus-based to bring the consensus-based work we built for our control plane into Vitess. Cool, that's all I had for you guys. All of this talk was roughly based on a blog that we wrote. Sorry. I would recommend. So this was roughly based on this blog that we wrote. This covers our entire control plane, what sort of choices we made, what sort of automations we do, what is our orchestrator, etc. I'll share the link of this in the slides. Thanks so much.